Hello and welcome back to another IB Math speedrun with me, Vince. In today's speedrun, we're going to be going through chapter 9.5, which is all about the vector product. So let's jump right in. So what is the vector product? So we already covered the scalar product of two vectors, which we denote as A dot B, or the dot product, and this outputs a single number. But the vector product is a bit different because the vector product actually gives us another vector. So the vector product is simply A multiplied by B, and this is equal to the new vector, and let's write that out. This is equal to A2B3 minus A3B2. This is A3B1 minus A1B3, and the Z component will be A1B2 minus A2B1. So this is, one definition of it, but another definition, which you can see if you try and plot some vector products geometrically, is that, a bit slow, is that this is also equal to the absolute value of A times the absolute value of B, or the distance, sine theta, where theta is the angle in between them, times n, where n is a unit vector whose direction is perpendicular to both vectors. It's given by the right hand rule. So if you have A, B, so if you stick out your three fingers of your right hand, and you have A going this way, B going this way, well then N will be going this way, perpendicularly to them. So yeah, some properties of the vector product include that A times B is equal to negative B times A, so this time it actually matters which order you multiply the vectors with, but this is simply for the direction of the resultant vector. Since if you swap B and A, then the direction of the vector changes. Next, A times B times C is equal to A times B times C, so that holds true still. Lambda A times B is equal to still lambda A times B is still equal to lambda A times lambda B. And finally, A plus B times C is still equal to A times C plus B times C. And so when we do a combination of three vectors, say A, B, and C, and we use both the scalar dot product and the vector product, this is called a mixed product, and this has some very interesting properties. So for example, this is equal, actually let's change that to the times and this to the dot. So this is equal to B times C dot A, and it's also equal to C times A dot B, and it's equal to negative A times C, since of course we swap these two around, so negative direction times B, and the same for all the others. So some interesting geometry, which I think you need to know, is first of all, if you have a parallel pipe, a 3D parallelogram with this kind of thing, where this vector here is A, this vector here is B, and this vector here is C, then the volume of this is given by the absolute value of the mixed product A times B dot C. So that's how you can find the area of this parallelogram. And the same holds true for, say, a triangle-based pyramid. If instead we're only finding this triangle-based pyramid over here and ignoring the rest, then it's simply, let's think. This triangle here is half the size of the original parallelogram, so it would be 1/2. And then the volume of a pyramid is 1/3. So 1/2 times 1/3 times A times B dot C, which is equal to 1/6 A times B dot C. So this triangle-based pyramid is 1/6 of the volume of the parallel pipe. So with that being said, we can now jump into some questions. So I will be doing the I'll do the even ones. So today I'm feeling quite even. So first, find the vector product of the following vectors using the algebraic definition. And first, we have C is equal to I plus J, and D is equal to 3I minus 2K. And then after that, we have P is equal to 1/2 I minus 3/4 J plus K, and R is equal to I minus 2/3 J minus 2K. So let's do the first one first. We have I plus J and 3I minus 2K. And so we know the vector product is equal to A2B3 minus A3B2, A3B1 minus A1B3, and A1B2 minus A2B1. So if we substitute these values in, A2 is 1, B3 is negative 2, so this is minus 2. A3 is 0, so this is just 0. Next, A3B1. A3 is 0, again. A1 is 1, B3 is negative 2. So we have 1 times negative 2 times negative 1, which is 2. And then A1B2 is 0, minus A2B1, so that's 1 times 3. And 1 times 3 is going to be 3. Yep. So the resultant vector should be negative 2, 2, and actually, sorry, this should be negative 3, since this was on this end. So it should be negative 2, 2, negative 3 as the resultant vector. And if you want to check, this will be perpendicular to either of these two vectors. Actually, let's just check that right now. So we have the vectors 1, 1, and 0, and negative 2, 2, and negative 3. And we can use the scalar product to find the angle in between them. So we have A1B1 plus A2B2 plus A3B3 divided by absolute value A times absolute value B is equal to cosine theta. So we have A1B1, so that's negative 2, plus A2B2, which is 2, minus 0 times 3 is 0. And as you can see, negative 2 plus 2 plus 0 is equal to 0. And so no matter what the magnitude of the vectors are, this will be equal to 0, so cosine will be equal to pi over 2. So these vectors are perpendicular indeed. Okay, and then let's move on to the next one, and that is over here. So we have the vector 1/3, negative 3/4, and 1. And we need to multiply this by 1, negative 2/3, and negative 2. So this will be equal to A2B3. So A2B3 is 3/2 minus A3B2. So that's plus 2/3. Next is A3B1. So A3B1 is 1 minus A1B3. So that's minus plus 2/3. And then finally, we have A1B2, which is negative 2/9 minus A2B1. So that's plus 3/4. So if we add these up, we have 3/2 plus 2/3. This is equal to 9 plus 4 is 13 over 6. 1 plus 2/3, 5/3, and then negative 2/9 plus 3/4 is equal to 8, negative 27. So 27 minus 8 is 19 over 36. So I got that as my answer. Ooh, it's a bit different to what we have here. Maybe I copied down one of the vectors wrong. I think I did copy down one of the vectors, one of the answers. Ah, sorry, I put 1/3, but it was supposed to be 1/2. Sorry about that. So anyways, we need to correct these two. So first, this should be A1, B3. So 1/2 times negative 2 is 1. So this is 1 plus 1. It's 2. And this over here should be 1/2 times negative 2/3, which should be negative 4/3. So now let's make the appropriate corrections. So we have 2. And we have negative 16 plus 9, which is negative 7 over 12. 1/2 times 2/3. Oh, this is 2/6. Oops, why did I add them? Which is 1/3. Negative 1/3 plus 3/4 is only 5 over 12. So yeah, that was the answer. Nice. Okay, let's move on to the next question. And so the next question states that a parallel pipe, a triangle with the vertices A is equal to 1, 4, 2, B is equal to negative 2, 0, 3, and C is equal to negative 1, 2, 4 is given. So first, find the vectors A, B, and AC, and next, use the vector product to find the area of the triangle. Okay, so first let's find the vectors A, B, and AC. So AB will be equal to, it's just simply B minus A, so 3, 0 minus 4, 3 minus 2, and then AC is equal to negative 2, negative 2, 2. So if we use the vector product to find the area of a triangle, remember the vector product, if we have two vectors, say A and B, the resultant vector will have the magnitude of this parallelogram over here. So we just need to find that resultant vector. So this is equal to 1/2 times AB times AC. And there's like, I guess there's a little trick we can use. Can we use it here? I think we can. Because remember that we can rewrite this as A, B, well in this case it's AB, AC, sine theta. Oh, but we would need to know the angle between them. Okay, so I guess it could be better to just take the actual algebraic method of the vector product. So, unless we want to do dot product. So, anyways, we have 1/2 times AB times AC, so we have 1/2 times A2 times A3 minus A3 times A2. And then here we have A3 times A1 minus A1 times A3. And then finally here we have A1 times B2, minus A2 times B1. So we have 1/2 of the distance of -6, 4, and -2. So, hold up. Did I copy down a vector wrong? 1, 4, 2, -2, 0, 3, -1, 2, 4. -3, 4, 1, -2, 2, 2. Okay, that's okay. So we have the book's made an error. The book's made an error. Okay, so this answer should be correct because the book forgot to multiply correctly. So this is equal to 1/2 times the square root of 6 squared plus 4 squared plus 2 squared, which is equal to 1/2 times the square root of 36 plus 16. 36 plus 16 plus 4 is square root 56, and square root 56 is equal to 2 square root 14, I think. So the area of this triangle should be equal to square root 14. Nice. Yeah, so I think that the book is wrong. Anyways, on to the next question. It's the proofs. Okay, fine. So show the following properties of the vector product. And so the first property is A times B times C is equal to A dot C times B minus A dot B times C. Okay, well, it's interesting, at least. I mean, I guess we can just multiply this out, right? So we can transfer this because this should be the same as A times B times C. And then we can go that this is equal to A2 times B1 C2 minus B2 C1 plus A3 times B1 C3 minus plus A3 C1 this is B3C. This should be minus B3C1. Okay, wait. Because let's write out this multiplication first. So this is A times B2C3 minus B3C2. This B3C1 minus B1C3. And this is B1C2 minus B2C1. So if we multiply this, this would be A times, this would be equal to A2 times B3 times this 3, B1C2 minus B2C1 minus A3 times B3C1 minus B1C3. Over here we have A3 times B1, so B2C3 minus B3C2. This is minus A1 times B B3, which is B1C2 minus B2C1. Then here we have A1 times B3C1 minus B1C3 minus A2 times B2C3 minus B3C2. Sorry, you can't see that. Sorry about that. Anyways, let's continue now. And so for this side, we've already expanded this, so let's try and expand this side over here. So what would this be equal to? Well, we have A dot C, which is A1C1 plus A2C2 plus A3C3 times B. So that would be equal to A1C1 times wait. Well, this would not be, not be a vector, I guess, but so yeah, this would be equal to A1C1 times plus A2C2, right? Yeah. This is A1C1 plus A2C2 plus A3C3 times B. B1. No, this would be B. So this would be equal to A1C1 B1 plus A2 B1 C2. Yeah, because we're just multiplying a scalar to a vector plus A3 B1 C3 minus A dot B. So this is A1 B1 C1 minus A2 B2 C1 minus A3 B3 C1. So that cancels out. A3 B1 C3. So we can group these terms now. So here we have A2 times B1 C2 minus B2 C1 minus A3 times B1 C3 minus B3 C1. And if we compare these two, here we have B1 C2 minus B2 C1 and then B3 C1 minus B1 C3. Sorry, I accidentally swapped it around there wrongly. But anyways, we should get that these two are equal. And so we could expand the rest, but I won't do that here. But we should get that these two are equal. Okay, so that's a new proof we can use. And the next question is to prove that A plus B times C is equal to A times C plus B times C. Okay, I guess we can just do this by expanding it. So this is equal to A1 plus B1 times C. So let's write this out. A2 plus B2 and then A3 plus B3. And then we have times, of course, C1, C2, C3. So we get that this is equal to A2C3 plus B2C3 minus A3C2 minus B3C2. And then similarly, we have A3, which one are we? A3C1 plus B3C1 minus A1C3 minus B1C3. And then similar for the Z, you can expand that by yourself. Here we have A times C plus B times C. A times C will be A2C3 minus A3C2. And then B times C will be plus B2C3 minus B3C2. And just comparing these two terms together, these two are equal. And if we expand the rest, they will also be equal. Nice. Okay, the next question is, we have a parallel pipe. A, B, C, D, E, F, G, H is given. The vertices are A is equal to 1, 2, 1. B is equal to 2, negative 1, 0. C is equal to 2, 4, 2. and D is equal to negative 2, 2, 2. So, oh, sorry, no, that's not D, that's H. What? Where did I get that from? Oh, I wrote down the wrong coordinates. Negative 2, 2, negative 1, 3. That should be C is equal to 4, 5, negative 1, and D is equal to 4, 3. No, H is equal to 4, 3, 6. I'm seeing things. So, find the coordinates of vertex D and find the vectors that enclose the parallel pipe and see what is the volume. Oh, so they've given us a diagram, which is handy because otherwise I wouldn't know which one is D. So we have over here, this is A, B, C, D, E, F, G, H. And as you can see in a parallel pipe like this, we have A, B, and C, and so we can apply vector BC to A to get D. So vector BC is equal to 2, 6, negative 4. So if we add this to vector A, vector D will be equal to 2 plus 1 is 3, 6 plus 2 is 8, and then 1 minus 4 is negative 3. So this is the coordinates of vector D. Excuse me. And then, so find the rest of them. Okay, so we need to find E, F, and G. And we can simply get the transformation from D to H. So DH is equal to 3 to 4 is 1, 8 to 3 is negative 5, and negative 3 to 6 is 9. And we can apply this to all of vectors A, B, and C. So E will be equal to DH plus A. So this is equal to 1 plus 1 is 2. Negative 5 plus 2 is negative 3. 1 plus 9 is 10, so that's E. F is equal to, sorry, I'm writing these in vector form. I should be writing them in coordinate form. But anyways, F is equal to B plus DH, so that would be 3, negative 6, and 12. And then G would be equal to, sorry, you can't see that, 4, 5, negative 1. So 4 plus 1 is 5. 0, negative 1 minus 9 is 8. So I got these as the rest of the coordinates. Oh, it says the vectors that enclose it. Oh, I'm being silly, not the points. Okay, so for the vectors that enclose it, we can simply get the vectors of DH, DA, and DC. So DH, we already have that. DA is equal to negative BC, so that's DA, is equal to negative 2, negative 6, and 4. And then we need DC, which is equal to 3 minus 4. 4 minus 3 is 1. 5 minus 8, negative 3. And negative 1 minus 3 is 2. So these are the vectors that enclose it. So in order to get the volume, we can go A times B dot C. It shouldn't matter which way we do this. Like A dot C times B, A dot B times C should be the same. We need to get the absolute value, sorry. So let's just go A times B. Let's just use DH times DA. So this is going to be equal to negative 5 times 4 is negative 20. Plus 9 times negative 6, so plus 54. Next we have 9 times negative 2, that's negative 18, minus 1 times 1 times 4, so minus 4. And then finally we have 1 times negative 6 minus negative 5 times negative 2. So this is equal to, we have 34, negative 22, and 4. So if we have to get the cross product with C, which is 1, 3, 2, we have 34 times 1 plus negative 22 times negative 3 plus 4 times 2. So it's 34 plus 22 times 3, 66 plus 8. So this should be equal to plus 34 plus 8 should be equal to 108 units. Okay, that's not what the books got. Wait. They did DC times DA though, which is probably the easier one. Anyways, let's check where our errors are coming from. Hold on. What? How are they getting 0? Oh, no, that's fine, okay. Anyways. Should be negative 5 times 4 plus 9 times 6. This should be 9 times negative 2 plus 1 minus 1 times 4. And this should be 1 times negative 6 plus minus 5. Oh, this should be minus. Sorry about that. So we have negative, this should be negative 16 then. So in here we have negative 16 times 2. So we have 34 plus 66 minus 32, which is equal to 34 plus 66 minus 32 is equal to 68 indeed. So 68 is the correct answer. And then on to the final question. And the final question asks us to show that a dot b squared is plus a times b squared is equal to ab squared. Okay. What can we do here? So a dot b is equal to a1b. Let's just do this in 2 dimensions. So a1b1 plus a2b2 squared. So this is going to be equal to a1 squared b1 squared plus 2a1b1 a2b2 plus a2 squared b2 squared. Okay, a times b, or the direction of it, will be equal to a2b1 minus, oh, do we have to do this in 3 directions? Yeah, we have to. Oh, okay. Wait, there should be an easier way to do this then. We have a dot b squared. This is equal to a b cosine theta squared plus a times b is equal to a b sine theta. Oh, okay, so this isn't that hard actually. Times n, but n is only the direction vector. So if we're only getting the magnitude, here's a hint. If you're only getting the magnitude of a vector product, you don't need this n. You can go AB sine O as the magnitude. So since we are squaring this, we can rewrite this as cosine theta squared theta plus sine squared theta times a times b squared. And since this is equal to 1, this is simply equal to a times b squared. The magnitude of a times the magnitude of b squared. So that was all for the speedrun. I hope you enjoyed, and I hope to see you in the next one. See you then.